We're going to talk about section 7.2, and we're going to talk about angles and a new way of defining sine and cosine. So in your geometry days, angles usually come from like a triangle, so they're usually thought of as being between 0 and 180 degrees. But we're going to extend and expand that definition because it's too limiting. So we're going to redefine what an angle is, and then we're also going to learn a new way of thinking of sine and cosine, different than the SOHCAHTOA definition, what we'll call the right triangle definition. Now, the new definitions for the angle and for the sine and cosine aren't going to contradict anything that you've learned before, but it's going to open a door to more possibilities and broaden what we can do. So we are going to talk about an angle as having an initial side that is the positive x-axis. So we're going to imagine that our angle is going to start here. And so our initial side is the positive x-axis. And then we're going to imagine that a positive angle is going to go counterclockwise and a negative angle is going to go clockwise. So we can spin around however far we want, and then where we end up, that is going to be our angle theta, and the place where it ends is going to be the terminal side. So we have an initial side that is always the positive x-axis and a terminal side that is going to be where it ends. So we can also sweep through a negative angle. So again, starting with the positive x-axis, if we go clockwise, then this would be the terminal side of a negative angle. So we're going to allow angles to be positive or negative. Now we're also going to allow them to be more than just there's no limit to how big they can get. So if we start with our initial side as the positive x-axis, we could go all the way around. There's a 360-degree angle, and then even plus more. And so that would also be an angle theta. So if this part right there was, say, 45 degrees, then the angle that I just drew, the 360 plus 45, would make that be a 405-degree angle. So we can have any size angle that we want, positive or negative. So we will name angles typically with capital letters, A, B, C, but we're also going to use Greek letters like theta and alpha and beta. So by the end of the year, hopefully we'll be fluent in Greek. That's one of our goals. Now, coterminal angles are going to be two angles that have the same terminal side. Two angles with the same terminal side. So, for example, if we had an angle, say, of, we'll make it easy and say, here's a 90-degree angle. Initial side, terminal side. So going here, we say theta is 90 degrees. Now, we could also start with our initial side and go all the way around 360 plus another 90 would be 450. So we would say that that 90-degree angle and that 450-degree angle are coterminal. We could also start with the positive x-axis and go through, there's negative 90, 180. We could say that theta equals a negative 270 degrees is also a coterminal angle. So any angle has an infinite number of coterminal angles. Kind of crazy, but this is going to be fun. Okay, so now let's see if we can come up with a new way of thinking of sine and cosine. So we're going to look at the unit circle. And by unit circle, we mean a circle centered at the origin with radius 1. So you may or may not know from your Algebra 2 days the formula, the equation of a circle centered at the origin with radius 1 is x squared plus y squared equals 1. We'll use that down the road, not so much here today. But now what we're going to do is see what we can look at for an angle theta. So here's our circle, And you can see it's going to cross the x-axis at 1, 0, and the y-axis at 0, 1, and so on. So if we take some angle theta, so here's going to be our angle theta right here. And we're going to see that it intersects the unit circle. So our angle theta, again, has the initial side, the positive x-axis, and its terminal side is somewhere here in quadrant 1, but it doesn't really much matter. Now, we can see then that if we drop in this perpendicular right here, we have created, I'm going to redraw it here, we have created a right triangle with this angle theta. And we're in particular going to focus our attention on the x and y coordinates of that point right where it crosses the unit circle. So the x-coordinate of that point is going to be this horizontal distance on our right triangle. And the y-coordinate of that point is going to be this opposite side of angle theta. And because we chose this to be the unit circle, then our hypotenuse here is a radius of the circle, so it must be 1. So using our right triangle definition, we can say that the cosine of theta is going to be the adjacent, which is x, over the hypotenuse, which is 1. That is, we're going to say that x is equal to cosine of theta. Now remember, x is the x-coordinate of that point. In a similar fashion, we can say that sine of theta is going to be the opposite, which in our triangle is y, over the hypotenuse, which is 1. That is, the y-coordinate of that point on the unit circle is the sine of the angle. Is that making sense? So this xy coordinate of our point is cosine theta, sine theta, for the angle that that the terminal side of that angle intersects that point on the circle. Now, similarly, we can also say that tangent theta is opposite over adjacent, which is y over x, which in our new way of defining y and x, we can think of as being sine theta over cosine theta. So here's our claim. We're saying if you take a unit circle, so a circle centered at the origin with radius 1, then another way of getting sine and cosine, other than our right triangle definition, instead of having to draw a right triangle, we can figure out where does our angle intersect the unit circle, and the x-coordinate of that point is the cosine of that angle theta, and the y-coordinate of that point is the sine of theta. Furthermore, the tangent of that angle theta is going to be that sine theta over cosine theta. So this new definition is called our unit circle definition. It does not require a right triangle at all. It just allows us to figure out those values by finding the coordinates of a point on the unit circle. Now, this immediately extends and expands what we can do for sine or cosine. So if we were stuck in a right triangle, then we can really only find the sine or cosine or tangent of one of these acute angles. That is, we're kind of stuck in here in quadrant 1. There's no good way in a right triangle to figure out, for example, what is the sine of a 90-degree angle. But with our unit circle definition, this is no problem. We can say, oh, the sine of 90 degrees, we're going to look at that point where a 90-degree angle, where the terminal side of a 90-degree angle intersects our unit circle. We know the coordinates of that point because it's a circle of radius 1. The sine of 90 degrees is the y-coordinate of that point. And the cosine of 90 degrees is the x-coordinate of that point. And the tangent of 90 degrees is going to be the sine over the cosine. Oops, in this case, that would be undefined because we can't divide by 0. Now, that's something we could not possibly do in a right triangle. Nor could we, in a right triangle, do something like what is the cosine of negative 180 degrees? Well, we know how to do that in a unit circle. I mean, there's no way you could do that in a triangle. We're going to go 180 degrees. That's going to go in the negative direction. That's clockwise. That's going to take us to this point on the unit circle, where the unit circle is on the x-axis. The cosine of negative 180 degrees would be the x-coordinate of that point. It's going to be negative 1. The sine of negative 180 degrees would be the y-coordinate of that point, and the tangent of 180 degrees would be the sine over the cosine, and that's going to be 0. Okay. So let's see what we get. I'm going to slide down here a little bit. It says, what are the coordinates of the point where the terminal side of theta is 20 degrees, where the terminal side intersects the unit circle? So if we imagine our unit circle, and we're going to take an angle of 20 degrees somewhere over here, all we can say there is that the x-coordinate of that point is going to be the cosine of 20 degrees, and the y-coordinate of that point would be the sine of 20 degrees. And if we wanted more detail than that, then we could go to our calculator, make sure we are in degree mode, and we could get then that the cosine of 20 is 0.940, and the sine of 20 degrees is 0.342, using our calculator to get the sine and cosine of 20. So we talked about these. The sine of 90 is going to be the y-coordinate of that point where a 90-degree angle will intersect the unit circle, and so that would be 1. And the cosine of 90 would be the x-coordinate. The sine of 180 would be the y-coordinate of the point where a 180-degree angle intersects the unit circle, and that would be 0. And the cosine of 180 would be the x-coordinate, and the sine of negative 90 would be the y-coordinate of the point where our terminal side of the angle of negative 90 degrees intersects the unit circle, and that's going to be negative 1. Now, we can also see, let's just talk for a brief moment, because the sine, cosine, and tangent will come from which quadrant it's in, we can see that the sine and cosine of any angle in quadrant 1, so any angle between 0 and 90 degrees, both the cosine and the sine will be positive. And since the tangent is sine over cosine, that's going to make the tangent be positive also. In quadrant 2, where we have negative x values and positive y values, the cosine is going to be negative, the sine will be positive, and so the tangent, which is sine over cosine, will be negative. In quadrant 3, where the x and the y are both negative, we will get a negative cosine values, negative sine values, and since tangent is sine over cosine, it will be positive. And in quadrant 4, where the x values are positive but the y values are negative, the cosine will be positive, the sine will be negative, and so the tangent will also be negative. We'll use that down the road here. Now, notice that because of the symmetry of the circle, we can get relationships here between, say, sine 40 and sine 140. So let me draw a unit circle real quick. I'm going to put an xy axis on there, and we know that this is 1, 0. I'll put that to indicate that it's a circle with radius 1. Now, a 40-degree angle is going to be somewhere in here. So there's our 40 degrees. Now, 140 we could think of as being 180, and then back up 40 degrees is going to be here. So 140-degree angle is going to be here. This part right here would be a 40-degree angle as well. So the sine of 140, remember, is going to be the y-coordinate of this point, and the sine of 140 would be the y-coordinate of that point. And hopefully you can see they would be the same. So these would be the same. How about the sine of 220 and the, let's go sine of 220 and compare those. Or let's do this. Let's compare the cosine of 40 degrees with the cosine of 140 degrees. So here again, now at this point, the cosine is the x-coordinate of that point, which is right there, and the cosine of 140 would be the x-coordinate of there. Can you see that these distances here are the same, but because one is to the right, this would be a positive value, and the cosine of 140 would be the same distance to the other side. It would be the negative of whatever cosine of 40 degree is. Same number but opposite in sign. Now sine of 220, so if we think of 220 as being 180 degrees plus another 40 degrees, then this angle right here is 40. So the sine of 220 would be the y-coordinate of this point. Now, how would that compare to the sine of 40 degrees? Well, it's going to be that same number, but in the opposite direction. So the sine of 220 would be the negative of the sine of 40 degrees. Does that make sense? I think you got the idea. So I'm going to go on. So this is kind of what we're using here when we're talking about this idea of symmetry, is we're using what we call reference angles. So for any angle, a reference angle is the acute angle formed by the terminal side of theta and the closest x-axis. So let's see what we mean by this a little bit here. And it's different for angles in different quadrants. So if we take an angle right here, and suppose, let me pick that to be a little different. Let's do maybe, I'm going to call this to be, say, 30 degrees. So I'm going to say theta is 30 degrees. The reference angle for 30 degrees is this angle that goes from the terminal side to the closest x-axis. So in that case, I'm going to call it theta sub ref. It's going to be the same thing. The reference angle is exactly the same. Now, if I take an angle over here, say in quadrant 2, and I'm going to call this 150 degrees, so there's now the theta, then the reference angle is the angle that goes from the terminal side to the nearest x-axis. So this is going to be the reference angle. And it will be, since this angle all the way to the y-axis is 180, it's going to be 180 minus 150 is going to be a 30-degree angle. So the reference angle, remember reference angles are always positive and always acute and always go to the nearest x-axis. Never, ever, ever do they go to the y-axis. So if I take an angle down over here, and suppose we say this is theta, which is, say, I'm going to say 210, I'm just staying consistent there. So then the reference angle is going to be going from the terminal side to the nearest x-axis. This is going to be the reference angle. And we'll take the 210 minus 180 is going to make that reference angle be 30 degrees. I'm going to pick something that's not exactly the same number. I don't want to confuse you with that. So let me take an angle, say, down here in quadrant 4. So I'm going to say that that angle theta is 300 degrees. So the reference angle is going to go from the terminal side to the nearest x-axis. There's going to be the reference angle, and that's going to be 360 all the way around, minus that 300 is going to make that be a 60-degree reference angle. Okay, let's see what we can do with this next one to clarify these ideas. So I'm going to draw an angle that's a 130-degree angle. So this is going to start with a positive x-axis. So there's 90, and if I went all the way to the y-axis, that'd be 180. So I'm going to be somewhere over here is going to be our angle of 130. So there's theta equals 130. The reference angle is going to be this angle right here, and that's going to be 180 minus 130 is going to be 50 degrees. And the sine, so answering these questions over here, the sine of 130, because this is in quadrant 2, if I imagine now, whoops, I didn't mean to make that an eraser. If I imagine a unit circle coming around here, then the y-coordinate of this point is going to be here, is going to be positive. So sine of 130 will be positive. The cosine of 130, because we're in quadrant 2, the x value of a point on the unit circle there would be negative, and therefore the tangent of 130, because it's sine over cosine, that's going to be a positive divided by a negative. It will be negative as well. Okay, here is going to be our 220-degree angle. So there's 90, 180, all the way straight down would be 270. So I'm going to go over here is going to be our angle theta. So we're going, oh, I'm sorry, it was a negative 220. Let me change that. That would have been a positive 220. So let me redraw my axis, and let me do this in the negative. So there's negative 90, negative 180, all the way to here would be a negative 270. So after I've gone 180, I'm going to go another 40. This is going to be our angle theta. The reference angle is going to go to the nearest x-axis. So the 220 minus 180 is 40. It's always going to be positive. So our reference angle is 40 degrees. In quadrant 2, the sine of negative 220, because we're in quadrant 2, the y-coordinate of a point here is going to be positive. And the cosine of negative 220, the x-coordinate of a point in quadrant 2 will be negative, and the tangent of negative 220, because it's sine over a cosine, it's going to be a negative over a positive. That will be negative. 650. So let's see. If we go positive 650, there's 360. 360 plus 90 is 450, plus another 90 is 540, plus another 90 is 630, and another 20 is going to take us to 650. So there's our angle theta. Our reference angle is going to be to the nearest x-axis. It's always going to be positive. It's always going to be acute. Since I said this much was 20, I think that's going to make that be 70. And because we're in quadrant 4, the sine of 650, in quadrant 4, the y-coordinate is going to be negative. The cosine of 650 would be the x-coordinate, which is positive, and the tangent of 650 would be a negative over a positive, which will be negative. All right, let's do a negative 800. So there's negative 360. There's negative 720. So another 80 degrees will take us about to here. So there is our theta is equal to negative 800 degrees. So our reference angle is going to come back to the nearest x-axis. And I think that's going to be, we said, what, 80 degrees, I think? And because we're in quadrant 4, the sine of negative 800 is going to be negative, and the cosine of negative 800 is going to be positive, and the tangent of negative 800 will be negative. Okay. Let's see what we've got here. So here's another Greek letter for you, phi. And so we've got this green angle here is our angle phi that's in quadrant 1. So can we sketch 180 plus phi? So if we start, I'm going to do it with the yellow. So here's going to be our 180 plus phi. So if we go, imagine going to phi, and then 180 degrees is going to be a semicircle, halfway around the circle. So I'm going to come halfway around, and this is going to be our 180 plus phi. Now the sine of 180 plus phi is going to be the y-coordinate there. So that's in quadrant 3, so it's going to be negative. And in quadrant 3, cosine is also going to be negative. I should have done yellow for the next one. I'm going to do 180 minus phi. So I'm going to imagine that we're going to go 180. So let's see, or we can do it a couple of ways. We can go 180, which is all the way around, halfway around, and then back up a phi. So that's a negative phi, is going to put us right over here in quadrant 2. There's our 180 minus phi. And the sine of that, because we're in quadrant 2, is going to be positive, and the cosine in quadrant 2 is going to be negative. 360 minus phi, imagine going around the circle 360, and then back up phi is going to take us down here. There's our 360 minus phi. It's going to be this angle right there. And the sine, we're in quadrant 4, so the sine is going to be negative, that's the y-coordinate, and the cosine is going to be positive, that's the x-coordinate. Okay, one more little thing here. So here we've got a triangle, and we want to know how does the sine of theta compare with the cosine of 90 minus theta. So sine theta we know is the opposite over the hypotenuse, and so that's going to be a over c. Now if this is a right triangle, then all the angles add up in a triangle to 180. If we subtract off the 90, that's 90 left for these two to share. So if that's 90, then this angle must be 90 minus theta. And so then the cosine of that angle, 90 minus theta, is going to be the adjacent over the hypotenuse. The cosine of 90 minus theta is a over c. It's not a coincidence. The sine of an angle and the cosine of its complement are always equal to each other. All right, very good.